Okay, so here's the plan right now, 2.3, I got a peak of 2.4. Quiz prep, 2.1, 2.3, because that's gonna be your quiz. We'll have a post today. And then continue with 2.4, 2.5. You get the review sheet on Wednesday. Wednesday, we're taking the quiz on 2.1 to 2.3. There will be bonus problems. Next Monday is review, and next Wednesday is the test, and homework will be due. So this is the one I posted last week. This is 2.1 and 2.2 only. You know, I'm over here, I'm going, there's not gonna be, I'm gonna send me going, you know what, I'll see how far we get this up today, and it's like this camera right now, I'm all over the place. This is not practical to get all this in, so here's what I'm gonna do. So this is Wednesday. Friday is November 1st. Then you have the 2nd and the 3rd on Sunday. So November 4th will be the test. Homework due. On the 30th, we will review. Okay. And that means I'm going to give you the chapter 2 quiz here on the 28th. With bonus problems. And this will also give us a chance to finish up and complete 2.4, 2.5. It's got a lot of do this problem this way, but this one's a little bit like it, but not so much like it. There's a little twist to it. There's a lot of examples. So this is going to kind of, 2.3 will probably spread in both days. And 2.4 will definitely spread all over the place. And then 2.4, 2.5. Bottom line for you guys, the quiz is on the 28th, so that's next Monday. The test is on the following Monday, the 4th. No, you cannot vote to what day. That'll be Tuesday, Thursday, because that's actually voting day. November, wait. The 5th of November, so something I'll remember. These are the take a look. Okay. This is what's going to post again. I'm going to post it anyway. It's a big quiz. It's got lots of stuff in it. Like one of the big salads on Seinfeld. First problem, just like 2.1, 2.2. Second problem, 2.1, 2.2. Third one, only decimal, 2.1, 2.2. And then 4, 5, and 6 are all 2.3. Simplified terms with radicals and basically dealing with imaginary numbers. Imaginary numbers. And then look at that friendly face right here, 8B for bones. So that's what the B stands for when you see this. Find the slope and the y-intercept. This one is a 2.1, 2.2. Solve for B. Or solve for B, solve for A, but it's vote. And then how about that? I'm sure you've seen that before. But it's a 2.1, 2.2 problem. That's the degrees turning Celsius into Fahrenheit. So what's the formula for turning Fahrenheit into Celsius? It is exactly like if you had X equal to everything over here on this side, then solve for Y. But that's the quiz that's next year. Back to this. Give me 3 problems that you would want to see. Number 2. Okay, here we go. Number 2, what else?
4,
2, 4, what else?
5,
5, that's it. So 2. 6 over 5 minus 2x over 3 plus 19x over 12 equals 3x over 20 minus 3. Five over x minus 5 minus 4 over x minus 6 equals 2 over x squared minus 11x 30. And number 5. 64 times, so I just 41. Undo the fraction. Step 1, simplify both sides completely. Undo fractions if you have them. So we need the least common denominator. So for a 5 and 3, that would be a 15. Now you have a 15 and a 12 and a 20. 15 and 12, well, that would be a 30. 12 and 30 don't go together. The next would be 45. Well, you can't make 12 into a 45. The next multiple of 15 would be a 60. 12 goes into 60. This is 12 times 5, and this is 4 times 15. So we can make a 60 out of a 15 and a 12. So right now, for a 5, 3, and a 12, the least common denominator would be a 60. And guess what? 20 goes into that as well. 3 times 20 will also make 60. So the least common denominator that undoes all of the denominators is going to be a 60. So I multiply every single one by the least common denominator. 60, 60, 60, 60, and 60. Every term has to get multiplied by 60. Okay. Remember, the purpose is to undo the fractions. So we're going to reduce before we multiply. 5 goes into 60 12 times. 12 times 6 is 72. Minus, and again, from left to right and bring it down right underneath. 3 goes into 60 20 times. 20 times 2x is 40x. Plus 12 goes into 65 times. 5 times 19x is 95x. Equals 20 goes into 63 times. 3 times 3x, 9x. Minus 3 times 60 is 180. On the chapter 1 bonus questions that you had to come into office hours and do, there was a problem with fractions in it. And for the most part, did pretty well on it. Where the mistakes happened was right here when you did something over here on the right side of the equation, and you multiplied by the least common denominator, this one didn't have the x, but this one did. And that's not how the problem started. So it's kind of like keeping track of everything. It's like this TV show is so long, I forgot what happened at the very beginning. So I'll make it up and put it somewhere. And that is a common mistake. Details matter. It was a simple detail, and that caused a little few things that, like, forgetting to put an x here. because that one hasn't. And that's why you want to go from left to right and right underneath. So you make sure everything is accounted for. So simplify both sides before you start moving things left and right. You can still simplify this. 72. Negative 40x plus 95x is positive 55x. Equals 9x minus 180. Both sides are simplified. Now we want to separate the variable from the constant. We want to get variables on one side. Focus on the variable first. So we either take the 55x and subtract it from both sides, take it to the right, or subtract 9x from both sides and bring it to the left. So what do we want to do? Left or right? Right. Let's subtract 9x. And have 72. 55 minus 9 is positive 46x equals 9x minus 9x cancels out. And we still have a negative 180. And since we brought it to the left, we had to take the 72 to the right. Since it's a positive 72, we subtract 72. So we have a positive 46x equal to a negative 252. Divide both sides by 46. So let's see. I don't know if it goes in evenly, but at least I know they're both even. So it's going to be a negative, definitely. And that's 2 times 126 over 2 times 23. Then the big question is, does 23 go into 126? Well, that'd be no. So the final answer is negative 126 over 23. Final answer should be written in reduced fraction form. No decimals. Any questions? Okay. We got fractions again, so we want to undo the denominator. Well, on the left side, we have only one term in the denominator. We have perfect factors already. We have to undo it to multiply by at least common denominator. It has to have an x minus 5 in it, parentheses, x minus 5, to undo that x minus 5. It also has to have an x minus 6 to undo that x minus 6. So I'm hoping that this will factor into x minus 5 times x minus 6. So I'm just going to check. Does x minus 5 times x minus 6 equal, question mark, x squared minus 11x plus 30? Because if it does, then that multiplied together will undo that denominator as well. So x times x is x squared. X times negative 6 is negative 6x. Negative 5 times x is negative 5x. And negative 5 times negative 6 is positive 30. So we have an x squared. Negative 6x minus 5x is negative 11x in the middle, and a positive 30. So sure enough, these two multiply together will undo that denominator because x minus 6 times x minus 5 are the factors. Otherwise, if they didn't multiply and equal that, I would have to figure out what the factors are. Because I need a least common denominator that undoes all of the fractions. And they're not going to do that to us in 2.1. they're going to give us a problem where the right side denominator is going to use the factors up from the left side. Should you assume that when we're in 2.5? No. But for 2.1 and for your quiz on Monday, you're good to go. It doesn't hurt to rewrite it though. So that you can see how these things are going to happen. So we now have this is 5 times, or 5 over x minus 5, minus 4 over x minus 6 equal to 2 over, this is x minus 5 times x minus 6. One last thing before I begin. Because the denominator has x's in the denominator, I need to be concerned about something that we call extraneous solutions. We're not allowed to divide by what? 0. So I'm solving for x's. I could get an x that I can't use in the denominator because it makes the denominator 0. What would make x minus 5 equal 0? 5. So here's the deal. If we get x equal to 5, we have to throw it out because we can't use it. And I'll show you what we're going to get is we're going to get an equation that doesn't have denominators because we're going to undo them. So the equation that we actually solve, 5 will work, but in the original problem, I can't use it. It'll work in the new problem, but it won't work in the original problem. So we have to think about what we're actually going backwards to solve. What can this x not be? It can't be a 6. Because if I get a 6, I can't put it back into here. So if I get a 5 or a 6, I got to throw them out. Anything else that we get will work, provided we did everything else correct. So now we're going to multiply everybody by x minus 5 and x minus 6. And I seriously hope you actually show this work. X minus 5 times an x minus 6 here, an x minus 5 times an x minus 6 here, and over here, an x minus 5 times an x minus 6 here. And over here, definitely that's where it's forgotten. They forget to put it there. So you can see what reduces. Over here, x minus 5 reduces, and we're left with 5 times that x minus 6. No more fraction. The x minus 6 reduces, and we're left with a minus 4 times that x minus 5 equal to x minus 5 reduces, x minus 6 reduces, we're just left with a 2. We're still in step 1. Simplify both sides, undo fraction. Now we're simplifying. 5x minus 30. Distribute negative 4. Negative 4 times x plus 20 equals 2. Five x minus 4x is 1x. Negative 30 plus 20 is negative 10 equals 2. So you add 10. X is equal to 2 plus 10, which is 12. We didn't get a 5 or a 6, so we're good. So you can check and see if you got it right. Plug in 12. This would be 5 over 12 minus 5 minus 4 over 12 minus 6, and that's supposed to equal 2 over 12 to the second minus 11 times 12 plus 30. So this is 5 over 7 minus 4 over 6. And that's supposed to equal 2 over 144 minus 132 plus 30. So this is 5 over 7 minus 2 over 3 equals 2 over, that's 12 plus 32, so 42. What's a common denominator for 5 or for 7 and 3? 21. So we have to multiply this by 3 over 3. That gives us 15 over 21. And this one times 7 over 7. And that gives us 14 over 21. And this is 2 times 1 over 2 times 21. So that's 1 over 21. What's 15 minus 14? 15 over 21 minus 14 over 21 is 1 over 21 equal to 1 over 21. So when I plug in 12, it works. That's really easy. If we want the slope and the y-intercept, basically b, y equals mx plus b, solve for y. So the first thing you have to do is get x on the other side. We want to get y by itself. So since that's a positive 64x, we subtract 64x from both sides. Negative 40y equals negative 64x plus 104. And then we divide each one by negative 40. So that positive y equals a negative over a negative is going to be a positive. And a common factor of 64 and 40 is 8. This is 8 times 8 over 8 times 5. And then you have the x. And positive over a negative is going to be a negative. And common factor of 104 over 40 is going to be 8 again. So that's going to be 8 times 13 over 8 times 5. So here the 8's reduced, so we're left with y equals 8 times x minus 13 over 5. So the slope is 8 over 5, and the y-intercept is negative 13 over 5. You don't put x here. X is not part of the slope. The slope is the m, the coefficient of x. Simplify fractions. Bonus question next Monday. This kind of question on the quiz is a bonus question on the quiz. But the first one that we did, that'd be a regular quiz question. Okay. We get more practice today. And it's story time. Can anybody fill in the blank? Anybody fill in the blank? Blank is the mother of invention. Frank Zappa? No, he's the mother of prevention. Oh, that was his band name. Necessity. The first person I think that's gotten in many medicines. Necessity. Need. Let somebody come up with a brand new crazy idea. There's a need for something. Why irrigation? Because they were thirsty. Why planting things in crops? And because they want to make money. Because people are hungry. And that because we want to explain stuff. Well, how do we get the concept from that? Because we need it to count things. Where did it all come from? Let's go way back when to the Stone Age. And you're the hunter for the Stone Age people, the tribe. And your job is to go out and kill some saber-toothed rabbits. Big, ugly. Rabbit season. And how many rabbits are you supposed to go out and get when there's no numbers that exist? You just go get a whole bunch, you just bring back one. I mean, either people starve or you got too much and they're rotting. You don't have ways to preserve them yet. You can't, you don't have dehydration machines and you don't have any ideas about smoking things and jerky yet. So what do you do? Well, you kind of, and again, I'm making this stuff up. I wasn't there. A one-to-one correspondence. Let's just make it simple. You take an old rabbit skin. For every person in the tribe, let's just say these 4 people or my family or whatever. I put one rock in the rabbit skin. So I go hunting, and every time I kill a rabbit, take a rock out of the rabbit skin, and the rabbit skin's empty. I have enough rabbits to feed my family. That's a one-to-one correspondence. But when the family starts getting bigger, that's a heavy sack of rocks to go carry to kill rabbits. So there's got to be a better way. So they start thinking a little bit about how to carry a sack of rocks, not so much physically, but mentally. And they start, when you think about it, you assign a number, some kind of counting, some kind of arrangement, some kind of order to the people in the tribe. Maybe you memorize their names. I don't know. But if you just count, you don't have to memorize a whole bunch of names. There's 10 people in the tribe. I have to count 10 rabbits. Because you don't know the rabbits' names. But anyway, the counting numbers, or the natural numbers, is the first set of numbers that appear in our search for answer out of necessity. The counting number. Also known as the natural numbers. Are the set of numbers that start with 1, 2, 3, 4. They go on forever.
And when you think about how do we remember that name, counting number of natural numbers? Well, naturally, what do you teach a little baby to start counting with when you pick up their fingers? You put their hand, pick up their fingers. What number do you start with? One. You don't pick up the fingers, start with 0. You 1, 2, 3, 4, you count all the way to 10. So naturally, you start the counting numbers with 1, 2, 3, 4, 5. Counting numbers. And everything is going great. Except in the counting numbers, there is no number to represent the empty sack of rocks. When you start doing math, you want to be able to have an answer to any problem you come up with out of necessity. So 2 plus 2 is 4, that's a counting number. 5 minus 3 is 2, 2 is a counting number. 2 times 3 is 6, that's a counting number. There's an answer in that set. But when you go 5 minus 5, there is no counting number that's an answer for 5 minus 5. They don't have a number for it. There is no 0. And when you really think about it, there's no Roman numeral 0. They don't have a 0. I mean, they're making 10s with X's. The Greek used their Greek alphabet as their number system as well. So symbols, not just the number system that we use, our number system that we've been using for 1,000 years, well, now it's 1,024 years, is the Hindu Arabic number system. Actually, they've used it longer than we did. We stole it from them. We borrowed it. We've been using it. So. But the number system, the numbers that we make are from the Middle East. Up until then, they've been using in Europe the Greek system or even Roman numerals. They were working with that. The guy by the name of Leonardo of Pisa decided, no, you know what? I like their math better. He's wrote a book based on their algebra. He wrote a book based on their number system. And along comes everything we've got. Okay. The credit still goes to the Middle East. But the whole numbers is where 0 begins. That's the set that has the answer to 5 minus 5. Out of necessity, we discover that there's another set of numbers that begin with 0. Because it's not here. The Mayans had a 0. I mean, completely separate, another culture also developed their own independent number system. It happened all over the place. That concept of math, I believe again, I wasn't there, I don't have any. I just think math is discovered. As we come up with new problems, that we don't have an answer for, we discover other levels of mathematics that we never even thought of before. Questions that we don't know yet. I mean, are we done with technology? Technology keeps evolving and changing. We keep getting brand new things over. I mean, 25 years ago, there were no cell phones. 10 years ago, think about the cell phone you had compared to the cell phone you have now. What will it be in 15 years from now? It can't do any more than it does now. Your cell phone has more computing power than all the space machines. So what will it evolve into? Imagination and necessity are going to drive it. Are there going to be things that we wish we didn't get? Yeah. I wish I didn't have a smartphone. So much time was wasted on it. But it's going to happen. Wish we didn't have 0. If we didn't have 0, I might have more money. Because I can spend all the way down to 0. No whole numbers. So 0 takes care of everything until you go out to get a bunch of rabbits to feed your family. You have 5 people in your family, and then the relatives show up. Mother and father-in-law, so an extra 2 people. So you only have 5 rabbits, so you gotta go next door and you gotta borrow 2 rabbits. Borrow. Alone. 2 rabbits. So you have 5, you gotta borrow 2. So 5 minus 7. There's no answer in 5 minus 7. So there must be another set of numbers where 5 minus 7 has an answer. Because we come up with a problem that 5 minus 7 exists, there must be an answer somewhere. So that set of numbers is called the integers. From negative infinity to positive infinity. To the left, to the right. Now, if you look, every counting number is also a whole number. And every whole number is right here in the integers. It's like a family. These guys are part of this family, and these are part of that family, but it doesn't go this way. All right. Mama and Papa Caveman now need a divorce. Because, the in-laws is too much. So they have 5 rabbits and they have to divide by 2. If it was 2 divided by 2, they can get that. If it was 4 divided by 2, they can get an answer there. So 6 divided by 2, they can get an answer there. But there's no answer in the integers where you can take 5 and divide by 2. So there must be another set of numbers where 5 over 2 exists. Okay? Because there's no answer right now. If you have 2 times x equal to 5, there's no answer in an integer where this works. They stopped. So there must be another set, and that set is called the rational number. Now, this one comes with a definition. A rational number is any number that can be written as a fraction. The key word for rational number is ratio. Rational number has that word ratio. Ratio means fraction. Five over 6. $37 over 12. Could be an improper fraction, could be a proper fraction. It could be an integer. Every one of the counting numbers is also a whole number. All of the whole numbers are also integers. All of the integers are also rational. 4 can be rewritten as 4 over 1, which is also, let's go 16 over 4. Same as 36 over a 9. I can change 4 into an infinite number of different fractions. If I can rewrite it as a fraction, it's a rational number. Rational numbers can be positive or negative. Negative 2/3. Rational numbers, another way that you can think of it is this. Any decimal, if you have decimal, any decimal that repeats or terminates, or let me say that backwards. that terminates or repeats. Terminates means it has a last digit. It has an exact last digit, like 0.25 is 1/4. I can change that decimal, that last digit of 5, into a fraction. Point 22222 repeating is 2/9 as a fraction. You can change any repeating decimal into a fraction. So repeating or terminating decimals can always be changed into fractions. So they're rational. And for a long time, this was all there was. Until about 300 BC. About 2,300 years. What if you didn't have a number that could be written as a fraction? Diagonal of the square. The Pythagorean theorem had been around for a long time. In the right triangle, the sum of the squares of the legs is equal to the square of the hypotenuse. The Pythagoras just proved it, but it had been around for a long time. The hypotenuse squared, x squared, is equal to the leg squared plus the other leg squared. So x squared is equal to 1 plus 1. So x squared is equal to a 2. Now we know 1 to the second power is 1, and we know 2 to the second power is 4. So we missed out on something. Something to the second power is equal to 2 here inside. Because it's got to be in between a 1 and a 4. So there's no fraction that works. So Pythagoras knew that it's a special kind of number, a number that didn't repeat a decimal and never had a terminating decimal. It's an irrational number. If you can't write it as a fraction, these are called rational, so the ones you can't do are the irrational numbers. Not be written as fractions. Because obviously, if you have ones that can, you're going to have ones that can't. It's inevitable. If these are decimals that terminate or repeat, these must be decimals that do not terminate or repeat. Non-terminating non-repeating decimals. in trig, we use one of those every single day, pi. Pi is an irrational number. It goes on forever, and it never repeats a pattern, and it never has it won't have a last digit. 3.14159, and it just keeps on going. Never repeats a pattern, never has a last digit. It goes on forever. An infinite number of non-repeating numbers. And they have supercomputers, and they have a network of computers, and they've calculated out to 1 billion places. They just keep on going. That's how they test the supercomputer speed. Another irrational number that you will meet this semester is the number e. When we do logarithms, e is the natural logarithm number, or natural exponent number. And it is approximately 2.71828, but it goes on forever, doesn't have a last digit, never repeats a pattern. So what do? We just use e. E plus 2e is 3 e's. E times e is e squared. So instead of using decimals, we just use e times e, e plus e. 5e minus 2e is 3e. When we use pi and trig, 3 pi minus 1 pi is 2 pi. Just like a variable. Because we would take an exact value over a estimated decimal value, a lot better than an estimate. The square roots, the ones that don't simplify. The square root of 2, square root of 3, square root 5, square root 6, square root 7, square root 8, square root 10, square root 11, keep on going. What did I skip though? Which one? I skipped the square root of 1 because the square root of 1 is 1, and 1 is rational. You would simplify the square root of 1. You wouldn't leave square root of 1. 1 is rational. What else did I skip? And the square root of 4 is 2. So 2 is rational. Always simplify anything that's in any kind of radical. I skip the square root of 9 because the square root of 9 is equal to 3. So I can write the square root of 9 as a rational number. So it's not an irrational number. But if it doesn't simplify completely, it stays as an irrational number. And all the way up until then, up until today, this has been your world. Your world's about to change. And your world has consisted of these sets of numbers that have belonged to one family. And that family has been known as the set of real numbers. All of these are in one family, one set, called the real numbers. If you make a number line, everybody in these sets that we've written up here, they're all in the number. There's an infinite number of irrational numbers on a number line. That's been proven. So when you think you've got infinity figured out, understand and remember, there's an infinite number of infinite numbers across from left to right, but there's an infinite number of numbers just to the right of 0. So which is bigger, the infinite number of numbers from left to right, from negative infinity to infinity, or just the infinite number of numbers from 0 to infinity? There's an infinite number of numbers from 0 to 1. There's an infinite number of numbers in between 0 and 1. Because if I start at 1 and I go halfway, 1/2, and I go half again, 1/4, That'll half again, 1/8, and that'll half again, 1/16. I can keep taking half forever. 1/32, 1/64, 1/128, 256, 1/512, 1/1024, 2048, 1/4196, 1/8394. You can just keep on going forever, keep taking half forever and never get to zero. There's an infinite number of numbers between 0 and 1. So that infinity is smaller than the other infinity. Infinity comes in all sorts of sizes. Good luck sleeping that. Or just watch Ant-Man on me. Because they got it going. Then along comes business necessities. And there's no real number that'll solve it. Because I'm going to take a real number and square it and get a -1. When I square something, it's the same thing. A positive times a positive, they have to be exactly the same thing. So if they're both positive, I'm not going to get a negative. Maybe I'm going to square a negative number. So a negative number times a negative number, well, that's a positive anyway. I'm not going to make a negative. Well, I can make a negative if I multiply a positive times a negative. But if I multiply a positive times a negative, I wouldn't be squaring it because they're not the same thing. It's impossible to square a real number and get a -1. +1 times +1 does not make -1. -1 times -1 does not make -1. A +1 times a -1 makes a -1, but it's not a perfect square because they're not the same thing. So there's no answer. But it still pops up in all sorts of actual life experiences, like wind shear. Okay, chaos theory. You start measuring weather patterns. So we have to be able to figure out how to solve something like this. So if the answer is not in the set of real numbers, it has to exist in the set known as the same name as the friends that I grew up with, the imaginary. It's a completely separate set from the reals. So the square root of x squared is equal to the imaginary number I. And when you make that imaginary number, put a hook on it. Because you don't want your i's confused with ones. Okay. So we see the square root of a -1. That's going to get replaced with an I. So now when you take the square root of a -4, here's what you do. When you simplify, step number 1, if you have a negative inside the square root, first thing you want to do is you want to poke out the I. Or poke the I out. And then you're going to simplify the square root. What's the square root of 4? 2. So the square root of -4 is just 2i. The square root of And here's why it happened. It's the square root of negative 25. So square root of negative 25 is how we take it apart. It's the square root of negative 1 times the 25. This is what's going on. And I can separate, because the rules of radicals, the square root of a times b can be separated into the square root of a times the square root of b. So I can separate this into the square root of negative 1 times the square root of 25. The square root of negative 1 is an I. And the square root of 25 is a 5. Now, when you write imaginary numbers like this, we don't write I5. We flip that around to 5 times I. You don't have to do all that. That's why I simplify and say, poke out the I. What's the square root of 25? It's a 5. Okay. So the square root of negative 225. Well, square root of the negative is going to be at I, poke out. What's square root of 225? 15. So that's 15I. That's why I gave you that list of perfect squares to fill out, perfect cubes to fill out, perfect fourth powers, perfect fifth powers. So if you printed that, build it out, you'd be better off. We have something like this. Square root negative 8. So this is poke out the I. And now you have to deal with this. 8's not a perfect square. So you got to figure out how to simplify your perfect square. Here's the rules about square roots. Make sure I have it right here. Simplifying square roots. Or simplifying radical. When I say radicals, we're going to talk about nth roots. Okay. So it could be a square root, it could be a cube root, fourth root, fifth root, whatever. Number 1, no perfect nth powers left inside and nth roots. So that means no perfect squares left in a square root, no perfect cubes left in a cube root, no perfect fourth powers left in a fourth root, and so on. Right now we're just focusing on square roots. So this is, poke out the I, you got square root of 8. The square root of 8 is the same as the square root of 4 times 2. That's the square root of 4 times the square root of 2. So what I'm saying is there is a perfect square that's a factor of 8. 4 goes into 8. 4 is a perfect square. So I factor 8 into 4 times 2. I can now separate square root 4 times square root 2. The square root of 4 is a 2 times square root 2. But don't forget, there's an I that you poke out, so it's 2 times I square root 2. And you put it all together. I'm going to clean this up in a minute. That is how it's always taught. That's not the way I teach it. The way it's taught is you find the perfect square that goes into the 8, and then you factor it, and whatever the perfect square is, that's what's going to break out. So when you have a square root of 32, what you have to think What's the biggest perfect square that goes into 32? And if you know your perfect square, you'll know that it's 16. So this is the square root of 16 times 2, and that's the square root of 16 times the square root of 2. And then you got 4 times the square root of 2. If you know your perfect squares. Or you can bust them out of jail. Jail method, you don't have to know the whole list of perfect squares or cubes or whatever. Maybe you don't know. But if you can make a factor tree in a square root jail, you need 2 of a kind. Square root, you need 2. So 4 times 2, I don't have a perfect square yet, I need 2 of a kind. But 4 is 2 times 2, and bring all the factors down straight across when you make that factor tree. So inside square root jail is an 8. To break out of jail, 2 of a kind, make a break for it. These 2 2s make a run for it. One of those 2s is going to get shot going over the wall. Shot and killed. Only 1 2 is going to make it out alive. In every case, whoever tries to escape, no matter how many there are, only 1 lives, everybody else dies. This 2 never even had a chance to break out. This 2 has to go back in his jail cell, back into square root jail. Square root of 8 is 2 square root 2. Okay? The square root of 32. Maybe you don't want to use 16 times 2 because you can't think of the perfect square of 16. So square root of 32. Give me 2 other numbers that will make 32. You can't think about 2 other numbers that make 32? 4 times 8? Well, you got 2 times 2, and that's 2 times 4. Break it down completely. So you got this 2, that 2, and then you got 2 times 2. This pair of 2s make a run for it. One is dead, the other one breaks out of jail. This pair of 2s make a run for it. One breaks out, makes it out alive. The other one shot and killed. This 2, all by itself, back in jail. The 2 2s that made it out alive, they hook up back, they're going to make a run for it. They're back together as a 4, square 2. When you have a cube root jail, cube root jail means you need 3 of a kind to break out of jail. To break out of jail, we need 3 of a kind. From now on, 32 is always going to be 2 to the 1 to the 2 to the 5th. Two times itself 5 times. So in cube root jail, these 3 2s make a run for it. Only one of them is going to make it out alive. That's the problem. Only one survives. Everybody else is dead. But of the escapees, potential escapees. The other 2 2s, they don't have enough. They need 3. There's only 2 of them. So they go back into cube root jail as 2 times 2, 4. Whatever breaks out, you multiply together. Whatever stays in, you multiply them back together. So if we had square root of 392. And if you don't know where to begin, how about it's an even number, start with 2. So this would be 2 times 196. And the good news is it's still even. So you got a 2 and you got a 2, and this will be 2 times 98. And that's still even. So you got a 2 and a 2, and you got a 2 times, that's a 49. So you got a 2, you got a 2, you got a 2, and 49 is 7 times 7. So they're all prime, so we're not going to factor each other. So you got 1, 2 that escapes. These two make a break for it. Oh, 1, 2 makes it out. 1, 2 left over. These two sevens make a break for it. So 1, 7 is going to live. So a 2 and a 7 both make it out alive. This 2 back in jail. The 2 and the 7 that made it out, multiply them back together, 14 square root. Now, if I know my square roots, right here, I would have been able to know this is 14 times 14. 196 is 14 squared. If I know my square roots, then I could have said, hey, there's a pair of 14s. A 14 makes it out, and there's a 2 stuck in jail. As soon as I got that pair, break it out. There's going to be a lot of people hurting really, really next week, or even on Wednesday. Because they're leaving early. They're really going to be hurting. They think if they think I'm just doing this and they know this. So make sure you know how to simplify your square root. If not, office hours. 2, whatever it takes. A lot of this is going to depend upon your ability to simplify your square roots, not decimals. Simplify square roots. Okay. So when you simplify your square roots, no perfect 10 powers left inside. No 2, no fractions left inside of the square root. Inside of the radical. And number 3, no radicals left in the denominator. And we'll get to that in our example. Here's learning this. When we deal with imaginary numbers, we replace anytime we end up with the square root of a negative. Square root of a -1 is going to be replaced with the imaginary number I. There's a little bit more here. But for now, your life has actually been, without you knowing it, this major union of both sets, real and imaginary, one set called the complex numbers. This is what you've actually been working with. And the complex numbers are written in this form, A plus BI. You've been working with numbers that are always, they can always be written in this form, where this is the real part, the real number part of the number, and this is the imaginary part. So something like 8 plus 3i. That's a complex number. Now, you haven't worked with something that looks like this, or -2 minus 5i, or something that looks like this, or 3 minus 1i. What you've been working with is stuff that looks like 12. But 12 has just been 12 plus 0i. The imaginary part has just been 0. So that means we don't write it. You've been dealing with pure real numbers. 1/3 minus or plus 0i. You've been dealing with just the 1/3. You've had no imaginary component to it. But now you're going to actually deal with complex numbers. 5/3 minus 2/7 i. Real and an imaginary part. Complex numbers. And here's the nice part. You're going to treat I just like a variable. 3i plus 7i equals 10i. Treat it just like a variable. It's not a variable, but you treat it like you're adding, subtracting, just like a variable. When you multiply, I times I is I squared. But that's as far as it goes, because you have to simplify that. This is what I mean. Last little piece right here. So here's the deal. I to the first, just like anything else to the first, is itself. I. Anything to the first power is I to the second. Take a look. I is the square root of -1. If I square both sides, there's my I squared. What happens if I square the square root? It undoes the square root. It undoes or cancels out, but undoes the square root. So the square root of -1 squared is just the -1. It undoes the square root. So what do I get? I get I squared equal to that -1. I to the first is I squared is -1. Always. So you would never leave I squared as an answer. You would write it as a -1. You end up with I squared, that becomes -1. So here's where it takes on. I to the third. So watch how we get the rest. I to the third is exactly the same as I squared times I to the first. Right? Because you add the exponents. 2 plus 1 is 3. And what did we just say I squared was? -1. So this is -1 times I. So I to the third is just -I. This is where I'm going. You're going to have to simplify I to the 3,281st. Let's go 83rd. 83rd. I to the fourth. So I to the fourth, that's exactly the same as I squared times I squared, using what we already know. 2 plus 2 is 4. What's I squared equal? That's a -1, and that's a -1. What's -1 times -1? 1. +1. So I to the fourth is always going to equal +1. I to the first is just I. I to the second is -1. I to the third is -I. I to the fourth is +1. Look what happens about I to the fifth. And look how we use the answers that we already got. And we use what we've already established. I to the fifth is the same as I to the fourth times I to the first. Right? 1 + 4 is 5. And what's I to the fourth? So 1 times I. So I to the fifth is just I. Feel like I've been there before. I to the sixth is the same as I to the fourth times I to the second. 4 + 2 is 6. So I to the sixth, what's I to the fourth? 1. And what's I to the second? And what's 1 times -1? So I to the sixth is -1. I, -1, -I, 1, I, negative. What's I to the seventh penalty? What? -I. I think I see a pattern. I to the seventh can be written as I to the fourth times I to the third. That's 1 times -I, and 1 times -I is -I. I to the eighth is going to be 1. I to the eighth is I to the fourth times I to the fourth, so 1 times 1. How in the world am I going to get to 3,000? Where is that? 3,283. Got to be a quicker way than keep writing. How many does it take to repeat this pattern? How many in the pattern? 4. It repeats every 4. So here's how you do this. You take this exponent and you divide by 4. You take the exponent, you divide by 4. The remainder is your new power. So 3,283 divided by 4. 4 goes into, can't go into the 1,000 place, so go to the hundreds. 4 goes into 32 8 times, so that's 3,200 in the hundredth place. So we subtract and we're left with 83 in the tens place. 4 goes into that 8 2 times, so that gets from 80. And then we have 83 minus 80, that's 3. So it's actually how many times in the ones place? 0 times in the one place. And then we have a remainder of how many? 3. 4 goes into 3,283, 820 times with the remainder of 3. So this is going to be the same as I to the third. The remainder is the new power. Divide by 4. the remainder is unit power. And what do we get when we get I to the third? Negative I. When you divide by 4, there are 4 possible remainders. A remainder of 0, because it went in even. A remainder of 1, remainder of 2, or remainder of 3. You should never get a remainder of 4 because then it would have gone in another time. So you'll never get a remainder of 4, but this is just the same as a remainder of 0. Everything to the 0 power is 1. That's one of our rules of exponents. Everything to the 0 power, then 0, is 1. Even I to the 0 is 1. Okay? So what I'm saying right here, 73-ish, that kind of problem is 73-ish. So back from the ancient times when we taught a class called Algebra 2, this is Algebra 2 review or your Math 2/Math 3 type of review. Now let's look at the homework examples. We're starting under that. Write the complex number in standard form. Standard form is the A plus BI. So 4 plus square root negative 9. So write it in standard form. So we want A plus BI. Well, you can't do anything with the 4, so bring the 4 down. And then plus square root of the negative, poke out the I. What's the square root of 9?
3.
3. So it's just 4 plus 3i. Not 4 plus I3. You're going to treat it like a variable. You wouldn't write x3, you write 3x. So 4 plus 3 times I. Okay. Number 15. You don't pay attention to what you're doing, it'll be messy. We want to simplify and write the answer in standard form. There's nothing you can do to negative 8i. That's simplified. Minus I squared. You have to simplify the I squared. So this is minus 8i minus what is I squared? We have just made it negative 1. So it's minus, and then parentheses, the answer to this is a negative 1. What happens when you subtract the negative 1? So it's negative 8i. Now we have a plus 1, but they want it written in standard form. They want a, the real number, and then plus bi. So 1 minus 8i is your final answer. The real number and then the imaginary. That order is going to matter. And Now, if you notice, there are parentheses, but am I multiplying? And it's addition. Go over this every single semester, every single year, ever since I've been teaching since 1990. Just because you see parentheses does not mean you're going to multiply these together. Look in between. It's an addition problem. Don't do what you think it is. Do what it is. Because you see parentheses, so you start doing rainbows because you see parentheses. All you have to do is add them together. So they don't make it more difficult than it actually was. Where you start, though, is you start inside the parentheses. You always need to simplify before you even do anything like this. Simplify what you can before you do it. Simplify the radicals, always. So this first parentheses, there's a 7. That's a plus. Square root negative 18. Well, then I got to poke out the I. And I got to simplify the square root of negative 18. So that's a 9 times 2, and a 3 times 3, and a 2. So a 3 will break out of square root jail. So that's 3i, and a 2 that goes back in square root jail. 3i square root 2. Now, here's the book. They're going to write 3 square root 2i. Don't do it. Don't do it. Because it's so sloppy, it's going to look like the I is under the radical when I see you guys write it. And if it's under the radical, it's not the same thing. Even when the book writes it, sometimes I can't tell if it's inside the radical or outside the radical. When they write it behind. If you put it in front of the radical, now I know it's not inside the radical. So treat it like a variable, put it in front. There's less confusion when you're dealing with it and when I'm trying to grade it. And it's still plus 3. And that's still plus. Poke out the I, and then simplify the radical. 32 is 16 times 2. 16 is 4 times 4, and then you got that 2. There's my perfect square that breaks out, so a 4 lives. 2 goes back inside the square root. So I've done everything I can inside the radical. Now I'm going to go ahead and drop the parentheses. 7 plus 3i square root 2. When you have a positive and plus, the signs don't change. Plus a positive 3 is still positive 3. Plus a positive 4i squared 2. Positive 4i square root 2. Not multiplying, you just combine the like terms. And that's just all you do now. The real numbers. There's a 7 plus a 3. 7 plus 3, that's a 10. Then the imaginary parts. You have 3i square root 2. That's a 4i square root 2. They're like terms. They both have an I square root 2. So 3 of them plus 4 of them is how many of these I square root 2s? Plus 7 of those I square root 2s. If this was 3i square root 2 and this was 4i square root 3, you cannot add them together because that's a square root 2 and that's a square root 3. They're not like terms, so you would just have one. You'd have to write both of them. Plus 3i square root 2 plus 4i square root 3. You cannot add those together. They're not the same kind of radical. You have to write it like this. But because they're both square root 2s, 3 of those plus 4 of those, 7 of those. Gotta know how to combine the like terms. 42. Now we're doing some multiplication. You can see how they write it. They have the square root of 15 and I. Square root of 10 with an I. You can look like it's underneath, but it's not. You wouldn't deal with a square root I until you do polar coordinates. You can't take the square root of an I until you can change it into a function in terms of a radius and an angle theta. 42 is the square root of 3 plus the square root of 15, and I'm going to write it as plus I square root of 15 times the square root of 3 minus the I square root of 15. Here's what you want to be. This is going to equal 3 minus 15I squared. And not need to show the steps in the middle. And the reason why it's that quick is because it's the same exact terms. That's a square root of 3, that's a square root of 3. That's an I squared of 15, that's an I squared of 15. So A plus B times A minus B. And when I multiply them together, I get A squared minus B squared, the difference of two perfect squares. It's one of our special products. Now we still have to simplify that, but we'll get there in a minute. The rule for multiplying the square roots. The square root of A times the square root of B, you multiply the inside. A times B. So if we distribute, we get square root 3 times square root 3. So we're going to get square root 3 squared. Then we have a positive times a negative. So that's going to be a negative. And that's square root 3 times I square root of 15. And then we distribute positive I squared 15 times square root 3. Positive I square root of 15 times this square root 3. And then we have a positive times a negative, so that's going to be a negative. I square root 15 times I square root 15, so that's parentheses I square root of 15, whole thing squared. So when I square a square root, the square undoes the square root. So this is just going to equal 3. Or if you want to do it this way, square root 3 times square root 3 is the square root of 9. The square root of 9 is just 3. And then we have minus. Square root 3 times I square root 15 is I times the square root of 45. 3 times 15 on the inside, 45 on the inside. And this is plus square root 15 times square root 3, 3 times 15, that's another I square root of 45. And you can see why we don't have something in the middle, negative I squared 45, positive I squared 45, they end up canceling in the middle because it's A plus B times A minus B, it's always going to cancel in the middle. A minus, when you have two terms, two factors to a power, the I squared, the I gets raised to the power, and the square root of 15 is going to get raised to the power.
So I'm squaring that square root of 15. The square undoes the square root, so I just get 15 minus that 15, and I have times that I squared. So there's my 3 minus 15I squared. What's I squared? So 3 minus 15 times -1. So negative 15 times that becomes 3 plus 15. And that's an answer of 18. When you multiply, special word for this, conjugates. These two are conjugates of each other. They're exactly the same term. Square root for I root 15, I root 15. But one is a positive, one is a negative. When you have exactly the same term, both one's plus, one's minus. So maybe that's minus, that's plus. When you have conjugates, you will always get a squared minus b squared. And that will undo the complex number. You get rid of the imaginary part. You'll get rid of radicals when you do that as well. Because you'll always get a squared minus b squared. The perfect square. That's an important piece, the word conjugate. That takes us to 42. We'll continue on Wednesday. I'm still going to post a quiz prep. Do what you can get through. And also we'll have the answers on the back page or second page.